So friends, very warm welcome to you all. Now today we will start the next topic, that is semiconductor PN junction and the various devices and their applications. So first of all, we will going on to study under these objectives what is mean by that semiconductors, then doping term, then various types of semiconductors, then PN junction, then PN junction diode, diode biasing, VI characteristic and diode currents. So all these are the objective of our today's session. So we'll see one by one. Semiconductor, you are already familiar with this term. That is nothing but the material having its conductivity which lies in between conductor and insulator. That means it is not a good conductor as well as it is not a good insulator, right? And from that periodic table of the material, the best examples under this is silicon and germanium, that is having their conductivity, or we can change its conductivity, is it? So these materials in their pure form is also known as a semiconductors, while after adding external impurity with these, which is known as a doping, it becomes impure, we can say, and then they are known as extrinsic semiconductors. So for example, if the external impurity which is of trivalent in nature, examples are like we can say boron, aluminium, gallium, indium, etc., is added, then the form impure semiconductor is known as a p type of semiconductor. And in that p type of semiconductor, we can say the positive charge carrier, that is holes, are the majority and minorities are electrons. Similarly, when external impurity of pentavalent, an example is phosphorus, arsenic and antimony, etc., if it is added with the intrinsic semiconductor, then the form impure semiconductor is known as a N type of semiconductor. So in N type of semiconductor, the electrons, that is negative charge carriers, are the majority and minorities are now holes, is it? Now we'll see the PN junction. Whenever the p-type and n-type semiconductors are connected with each other, or we can say joined, the junction is formed between them, which is simply known as a PN junction, right? Now remember, during the formation of this junction, a self recombination between that some charge carriers which are very closer with each other at the edge of that junction gets recombined with each other, right? And once they gets recombined, stationary charge carriers, or we can say immobile charge carriers, gets accumulated around that PN junction like this. It is shown over here, the charge carriers with circle and remaining are the charge carriers without circle. So this circled one are known as stationary, or we can say immobile charge carriers, is it? Similarly, again, one more thing you can observe over here, if towards LHS side this material is of p type of semiconductor, purposely I shown the number of positive charge carriers, but at the same time very few number of negative charge carriers are also shown over here to indicate the majority and minority term. So in this p type of semiconductor, holes are the majority while electrons are the minority, and same over here in n type, the majority charge carriers you can observe are electrons and minorities are the holes. And that term also I mentioned over here, that is minority charge carriers for n type are the positive, or we can say holes. Okay, now once that stationary charge carriers gets accumulate around this PN junction, that region don't have the mobile charge carriers, and that's why that region is known as a depletion. Depletion means there is somewhat lack of what? Lack of mobile charge carriers, right? So that region is known as a depletion region, this one, where the accumulated charge carriers are immobile, or we can say these are the stationary charge carriers in this region. Now the accumulated charge carriers, it looks somewhat like, we can say, a charge capacitor. Right now generally we are showing the charge capacitor with one plate as a positively charged and another one as negatively. So the same this junction looks like that, is it? So this junction offers some potential because of this stationary charge carrier, and that potential, it is known as a barrier potential. Barrier means what? It is acting just like a wall. It will not going on to allow that remaining charge carriers to get recombined with each other, right now. So that region, it is acting as a barrier to whom? For the recombination of remaining charge carriers, right? And that wall have its own strength, we can say in our electronics language. So that strength is either, we can say, 0.3 volt or 0.7 volt, and that depends on which type of material is used for the manufacturing of that PN junction. So if it is germanium, then that barrier potential is of 0.3 volt, and if it is of silicon material, then that barrier is of 0.7. Remember these two. Now here I shown the equivalent of the diode. Whenever diode gets turned on, so it will be going to act like this. So this is known as a piecewise linear model of diode or equivalent of diode. See, small resistance is shown in series with somewhat voltage source. Is it VD? VD is nothing but diode voltage, and that is of either 0.7 or 0.3, we can say. And that RD, it depends on how much voltage is applied across that diode and how much current is flowing through that diode. Is it? That term we will see later on, why it is shown by small letter. That RD, it indicates it is a dynamic resistance. Dynamic means what? It is a variable. Variable means what? Or how it will going on to vary? So it will going on to change or vary by the amplitude of applied voltage and the flow of current through that diode, right? In detail we'll see in the characteristic. Now the diode biasing. Biasing is over here how we can connect that diode across the power supply. So see, both diagrams over here is nothing but forward biasing. Forward biasing means the anode of that diode, that is this terminal which is connected to p-type of semiconductor, is known as a anode, and towards the n-type semiconductor it is cathode. So if that p-type of material is connected to positive of DC source and n-type, that is cathode, to the negative, then it is known as a forward biasing. Okay, positive to p, negative to n. Same thing you can observe over here, even if the direction of the diode is reverse, but I also reverse the polarity of DC power supply. So both diodes are in forward biasing, both are same, don't get confused over here. And similarly another type of biasing, that is reverse biasing, just opposite to that of previous. If n type is connected, negative type is connected to positive potential, and positive p type is connected to negative potential, same thing you can observe over here also. So such type of biasing is known as a reverse biasing, right? Now the important terms, we can say the VI characteristic of PN junction. It is very important whenever you are studying semiconductors or a few semiconductor devices, right? So when that diode is in forward bias condition, means the applied voltage is positive to P and negative to N. How it will going on to act with the change in voltage, is it? So see, you will observe, purposely I have shown this curve up to the mentioned term as VFB, that is forward breakdown voltage of that diode. Already I mentioned that values, it is either 0.3 or 0.7 volt, that depends on the material used, that is either germanium or silicon respectively, is it? So whenever the applied voltage across that diode is less than that of that forward breakover voltage, that diode will not going on to conduct due to the barrier potential, that wall which is from across the PN junction, that will not going on to allow the flow of current, because that wall have its own strength. Whenever we will going on to overcome it, then and then there will be a flow of charge carriers, is it? And how to overcome it? That means the applied external voltage, it should be greater than that of the barrier potential, that is nothing but this VFB. Clear? So whenever the applied voltage will be equals to or greater than VFB, then and then there will be non-zero current through the diode in forward bias condition, is it? So first see, whenever that applied voltage is equals to VFB, a very small amount of current will start to flow, is it? And that's why I mention it as ID min, minimum diode current, and that will be going to occur at FB, VFB, is it? Whenever we will be going to increase that voltage with a constant step size, you will observe there is increase in current with exponential in nature. That current is not again linear like this. It is not a straight line, right? That's why what we can say, the device is not a linear device, it is non-linear device. And few terms we will going on to observe over here. So suppose I try to find out the resistance offered by the device between the applied voltage 0 to VFB, right? If the applied voltage is less than VFB, what I said, the amount of current flowing through the diode is 0 milliampere. Is it? Because we do not overcome that barrier potential. We have to find out the resistance offered by that diode, which we are calling it as a dynamic resistance, which is equals to delta VD by delta ID, change in voltage with respect to change in current through that device, is it, through that diode. So if the applied voltage is between 0 to less than VFB, that delta ID will be 0, no flow of current, is it? And in that case, how much will be the value of that small RD then? As delta ID is 0, we can see it will be of infinite. Clear? So the diode will going on to act as open if the applied voltage is forward bias but less than its forward breakdown voltage. It will not going on to conduct. Or in another way, we can say the diode will going on to offer the infinite resistance, that PN junction. Not only diode, any PN junction will going on to offer the infinite resistance if the applied voltage, even if it is forward bias, is less than its breakover voltage. Now the second case I taken at VFB to V1, means the change in voltage is between forward breakover voltage to V1. V1 is slightly greater than that of VFB. I mentioned that delta VD, it is only of 0.1 volt. Means for example, we taken if you consider a silicon diode, if its VFB is 0.7 volt, and if I take that V1 as a 0.8, now there will be surely increasing current greater than that of ID mean. ID mean is at VFB. That means there will be a non-zero delta ID. Is it? It will be very small initially. Delta ID, it will be very small. Correct. And that's why what we can say, as it is at denominator side, we can say that small RD, it will be of very high, because delta ID is very small. That small RD is inversely proportional to delta ID, right? So as delta ID is very small, we can say that small RD is very high. Okay. Now the next pair, that is between V1 to V2. Again, I will be going to change that applied voltage, forward bias applied voltage across that diode from 0.8 to 0.9 only. That means the change in voltage, the step size, I will be going to maintain as a constant, that is of 0.1. Over here you can observe, is it? Now in that case, you will observe the change in ID, that is from this point to over here. It will be somewhat more as compared to previous case, is it? Or we can say the change in ID will be from I1 to I2. Clear? In first case, it was from ID mean to I1, and that change is very small. Now in second case, the change is somewhat more. You can observe over here, the change in ID, it is somewhat more as compared to change in ID over here, is it? And that's why I mentioned here the delta ID as a high, okay, as compared to previous case. And that's why what we can say, that as that small RD is inversely proportional, if delta ID is high, then small RD will be small, is it? The dynamic resistance offered by the diode between these 2 points, it will be somewhat small as compared to previous. Previously it was very high, and previous to that of it was infinite, is it? Now take the another pair, that is V2 to VD max. VD max, again that step size is 0.1 volt, is it? V2 to VD max. Now you can observe the change in current between V2 and VD max. At V2 that current was I2, and at VD max we can say that current will be ID max. So this is the change in ID, and you can easily observe that change in ID, it is very high as compared to previous cases. And as it will be very high, what we can say, the offered dynamic resistance between that 2 points, it will be very, very small, is it? So what is the conclusion from this characteristic, or what we can say, if there is change in voltage, with a constant step size across that device, there is no change in current with a constant step size. That means the change in current is not linear. The change in current is exponential. It will be going to increase exponentially, is it? Even if the change in voltage across that diode is constant or with the constant step size, is it? So what I have to mention over here, thus the resistance offered by the diode is variable, hence it is known as a dynamic resistance denoted by small rd, is it? In previous lecture, one of my previous lecture, while studying the resistors and that LED, I mentioned the dynamic resistance of PN junction devices. It is very small, is it? 1 to 2 ohm I mentioned over there, is it? This is the reason behind that, correct? So that resistance is known as a dynamic resistance as it is dependent on the applied voltage across that device. Okay, so also increase in current is exponential for linear increase in applied voltage. So these are our two important points after this discussion, right? You have to remember this one. Now the PN junction diode current, already I said that current was exponentially, but mathematically how it is to be denoted, is it? So see, you will observe this standard equation that ID equals to IO in bracket e raised to Vd by eta Vt minus 1. So this is the derived equation. So you have to remember this one. By using this mathematical expression, you can find out the value of current through the diode once you are that means if you know the value of applied voltage to that diode, is it? In this expression, we'll see what is that ID. ID is nothing but the diode current. IO, it is the leakage current which flows due to the minority charge carriers. That means even if the applied voltage is somewhat less than that of VB, ideally what we are saying, the flow of current to the diode is 0. But practically, if we observe, it is non-zero. It is very small, closer to 0, is it? And that's why, and that current is due to minority charge carriers, and it is known as a leakage current, that is IO. Then Vd, that is the applied diode voltage. Then Vt, it is a volt equivalent of temperature, which can be determined by using KT by E, and at room temperature the value of that Vt, volt equivalent of temperature, it is of 25 millivolt. Remember this one. As there will be increase in temperature, remember that if T gets increased, what we can say, the value of that Vt also will get increased, is it? And when that value of Vt gets increased, the value of leakage current also gets increased, right? Then what is that another term? It is there, okay, that eta is nothing but the mobility factor of the charge carriers, which is equals to 1 if the value of that eta is 1, if the diode is manufactured from the silicon material, and you have to take that eta equals to 2 if it is of germanium, right? Now the PN junction diode VI characteristic in reverse bias condition. If what is that reverse bias, that already I explained. If the p type of or anode terminal is connected to negative potential of DC source and cathode terminal to positive, then it is known as a reverse bias. So by this characteristic, you can observe again, if we increase that reverse voltage from 0 to onward, more and more negative, then what happens? A small amount of current flows through the device. Again, it is known as a leakage current, indicated by IO. Okay, the value of that IO, it is very small, right? And one more term I mentioned here, that is VBR. VBR is nothing but reverse breakdown voltage of that diode. The VBR of different diodes are different. So I mentioned here one example, that is for 1N4007, that VBR it is of 1000 volt. So in general, the reverse breakdown voltage of the conventional diodes, it is very high. So no need to worry about it, right? That means, okay, we'll see that term later on. So see again, one more thing, I mentioned here that knee voltage. It just looks like our knee, and that's why it is known as the knee point or knee voltage. So at knee voltage, what happens? The reverse breakdown of that PN junction occurs, and infinite amount of current starts to flow. Infinite means what? It will be not exactly infinite, but it will be equals to the maximum current providing capacity of that source, which is connected across the diode in reverse bias condition, is it? And because of that very high current, the device gets damaged permanently. The PN junction diode gets damaged permanently. We can't reuse it later on. So from this discussion, what care you have to take whenever you will be going to use any diode in any application, just read its VBR. This VBR, again, one more term is there, and that is nothing but PIV, peak inverse voltage handling capacity. You might have learned it whenever you study the application of diode as a rectifier, peak inverse voltage handling capacity of that diode, is it? So whenever you are applying somewhat reverse voltage across that diode, the care you have to take, the reverse voltage, it should not be equals to its PIV or VBR. Otherwise, there is a chance of damage of that device. Device will get surely damaged, is it? But as already I told, that value is generally very high, so no need to worry that much about this VBR. So here we can take one example. If we consider a 230 volt RMS, if it is applied across the diode directly without any step down, by considering the same diode, that is 1N4007. So here this diode still it will not going on to damage. Why? Because even if it is 230 volt RMS, that means very high AC voltage, generally we are saying its peak value is 325. Vrms equals to Vm by root 2. By that formula you can determine the value of Vm of our 230 volt RMS 50 Hz signal. So that Vm, that will be equals to root 2 into that 230. So that value will be around 325 volts. Means how much peak negative voltage we are applying to this diode. If 230 volt RMS is directly connected across the diode for rectification purpose, we can say how much reverse voltage maximum we are applying, that is peak voltage, and that is of minus 325. Still that minus 325, it is very small as compared to this rating given for this diode, that is 1000 volts. So it will not going on to damage, is it? So this is just for your basic knowledge, that's why I taken that example. So here I will going to summarize. You might have understood about what is semiconductors, what is mean by that doping, then types of semiconductors, then what is PN junction, what is PN junction diode, then how we can bias the diode, or how it will going on to behave with the different types of biasing, that is forward biasing and reverse biasing, that you might have studied by using this VI characteristic and the diode currents. So I think you might have learned it properly. So thank you very much.